In this video, I'm going to show you how to use differentiation to calculate critical points. So first of all, what is a critical point? Well, a critical point of a function f of x is a point x equals c in the domain of f of x such that either the derivative f prime of c is equal to 0 or it is undefined. Now you might be wondering, why do we even care about critical points? Well, the reason we care about critical points is that they are candidates for maxima and minima of functions. Suppose we draw up a function that has several maxima and minima. How about something like this here? So suppose this function is f of x. Now forget about critical points and just look at this function and pick out what are the local maxima and minima. Well, those are the peaks and valleys in the graph. There's one there, there, and there. And at all these peaks and valleys, the derivative is equal to 0. You can tell that because the tangent line at each peak and valley is just a horizontal line like this. So all of the tangent lines at these peaks and valleys, they're all horizontal. So at all of these points, we have that f prime is equal to 0. The derivative is equal to 0 at each one of these points. Okay, so critical points are starting to make a bit more sense. We understand how the condition f prime of c equals 0 relates to being a local max or minimum of a function. But why would we also care if the derivative is undefined? Isn't the tangent line horizontal at any local max or min? Well, not necessarily. Consider, for example, an absolute value function. An absolute value function just looks like a V shape. And at the minimum here, the function is pointy, which means it's not differentiable there. So let's label that. Here, f prime is undefined. So if we just searched for points where the derivative is 0, then we wouldn't have found this minimum here. So that's why we need that other condition, f prime of c is undefined. Now one last word of caution before we move on. Notice that for a point to be a critical point, it has to be in the domain of the function. So if the derivative is undefined at a point, but say the function is not defined at that point either, then we don't count it as a critical point. Because there's no way it can be a maximum or a minimum of the function if the function isn't even defined there. So to sum it up, for a critical point c, we require that f of c exists, and either f prime of c equals 0 or f prime of c is undefined. Now let's get into some examples. We want to compute the critical points of the following functions. First starting with f of x, which is equal to x squared minus 4x. First of all, we take the derivative. So using the power rule, we find that f prime of x is equal to 2x minus 4. And we see that f prime of x is defined everywhere, so there aren't any critical points due to f prime of x being undefined. And we see that the derivative is defined everywhere, so there aren't any critical points due to the derivative being undefined. And we see that the derivative f prime of x is defined for all values of x, which means there aren't any critical points due to the derivative being undefined. But what about when the derivative is 0? Let's solve that. If f prime of x equals 0, then 2x minus 4 equals 0, which means 2x equals 4, which means x equals 2. And 2 is of course in the domain of this function, so there is a single critical point, x equals 2. Okay, how about the next function, g of x equals 1 over x. Again, let's start by taking the derivative. And we'll do that using the power rule. So first of all, let's write this as a power. 1 over x is just x to the negative 1. So that means g prime of x is equal to negative 1 x to the negative 2, which can be simplified to just negative 1 over x squared. So is the derivative undefined anywhere? Well, yes. G prime of x is undefined at x equals 0, because that would make the denominator equal to 0. But remember, if x equals 0 is a critical point, then it also has to be in the domain of g. And that's not the case here, because x equals 0 also makes a 0 in the denominator of the function g of x. So the derivative is undefined at x equals 0, but x equals 0 is not in the domain of g of x. And that means x equals 0 is not a critical point. Okay, so again, no critical points due to the derivative being undefined. But how about where the derivative is 0? Well, that would mean 1 over x equals 0, but that equation has no solution. So no critical points there either. So it looks like we don't have any critical points, and that's our final answer. No critical points. Okay, last example on this slide, h of x equals the cube root of x. We'll start by taking the derivative, and again we'll use the power rule. So first of all, we'll write this function as a power. Cube root of x is just equal to x to the 1/3. So then the derivative, using the power rule, bring down that 1/3, and then x, and then subtract 1 from the power. 1/3 minus 1 is negative 2/3. And this can be simplified to 1 over 3x to the 2/3. Now again we see that h prime of x is undefined at x equals 0, because that would make the denominator here equal to 0. And x equals 0 is in the domain of h of x. We can plug in x equals 0 into this function and there's no issues. The cube root of 0 is just 0. So that means x equals 0 is a critical point. Alright, so now we've got a critical point from the derivative being undefined. And how about if the derivative is 0? Are there any critical points arising from that condition? Well, that would mean that 1 over 3 times x to the 2/3 is equal to 0. But the numerator of this fraction is never 0. So again, there's no solution. So that means there's a single critical point, x equals 0. Alright, here's the final problem. We're given a function f of x equals e to the x over sine x, and we want to compute the smallest positive critical point. So first thing we need to do here is we need to compute the derivative. And to do that, we will use the quotient rule. So f prime of x is equal to the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. And that's going to be all over the denominator squared. So we'll just go ahead and simplify that. Derivative of e to the x is just e to the x. That's being multiplied by sine of x, and then minus e to the x times the derivative of sine of x, which is just cosine of x. And that's all over the square of the denominator, so all over sine squared x. And just to clean this up, we can factor out a common term from the numerator. We can factor out an e to the x. So e to the x times sine of x minus cosine of x all over sine squared of x. Now that we've computed the derivative, let's take a look at where it's undefined. So if f prime of x is undefined, then the denominator has to be 0. So that would mean sine squared of x has to be 0. And then that means that sine of x has to be 0. And the solutions to this equation are just all of the integer multiples of pi. So x equals n pi, where n is an integer. But before we settle on these as critical points, let's make sure that our original function f of x is defined there. But actually, it's really easy to tell that these values of x would make the denominator 0 in f of x as well. These points came from the condition sin of x equals 0, so they're going to make sin of x equals 0 in the denominator of f. So although these points make the derivative undefined, these points are not in the domain of f. So they are not critical points. Okay, so no critical points there, but the other thing to check is, are there any critical points arising from the derivative being equal to 0? Well, if the derivative is equal to 0, then the numerator has to be equal to 0. So let's write that in. E to the x times sine of x minus cosine of x would have to be equal to 0. So that would mean either e to the x equals 0, or the other factor, sine of x minus cosine of x equals 0. But e to the x equals 0 has no solution because e to the x is always positive. So we focus on this equation here for solutions. And the way we can solve this equation is first by adding cosine to both sides. If you do that, you'll get that sine of x is equal to cosine of x. And then if you divide both sides by cosine, you get sine of x over cosine of x equals 1, which means tangent of x equals 1. One solution to this equation is x equals pi over 4. But we also have a solution whenever we add or subtract a multiple of pi. So we can write pi over 4 plus n pi, where n is an integer. Now, is our function f of x always defined at these values? Well, yes, sine of x is always non-zero at these values, so that means the denominator would be non-zero, which means that f of x would be defined. So these are indeed the critical points. But we are not done yet, because we want to find the smallest positive critical point. And to do that, why don't we list out some of these critical points here in increasing order. First of all, when n equals 0, we've just got pi over 4. And then when n equals 1, we've got pi over 4 plus pi. And we keep going onward that way. And then before pi over 4, when n equals negative 1, we've got pi over 4 minus pi. And we can keep going backwards that way. Now, pi over 4 minus pi, that's equal to negative 3 pi over 4. And then we've got pi over 4, and then we've got positive 5 pi over 4. That's what pi over 4 plus pi is equal to. So all the critical points to the left of pi over 4 are negative, and that means pi over 4 is the smallest positive critical point. So that's our final answer. Pi over 4 is the smallest positive critical point. And there we go, we're done. So now we know how to use differentiation to calculate critical points. And in the future, we'll see how we can tell whether a critical point is a maximum or minimum of a function, or neither of those.